All right, so we're going to be talking about inequalities in one triangle, so relationships between the sides and relationships between the angles. So here's a quick warm-up. Feel free to pause the video and solve these inequalities if you want. I'm going to go ahead and start going through them right now. So solving an equation and solving an inequality are very similar for the most part. This gets more difficult with certain types of inequalities, but for these simple linear inequalities, it's going to be very similar to solving an equation. There's just one or two things we need to keep in mind as we're doing them, and I'll talk about them as they come up. So for this one, we're solving for x. So we want to subtract 2 from both sides of our inequality. So we get 5x. And now here's the first thing we need to keep in mind. While we're solving, it's not an equal sign here. We need to keep the symbol that we're using, which in this case is the greater than or equal to symbol. We get 10 on this side. So we have 5x is greater than or equal to 10. Then we need to divide both sides by 5 so that we get x all by itself. And keeping our symbol greater than or equal to, we get 2. So this is our solution. X is greater than or equal to 2. We want to then graph that solution on the number line. So because this is a inclusive inequality, we are actually including 2 as part of our solution. It's not a strict inequality like this where we would say x is greater than 2, where 2 is actually not a solution. Since we do include it, we're going to use a closed circle on our number line. And then we're going to shade in the direction that it represents our solution. So we want to know the values that are greater than 2. So that's going to be this direction on our number line. So we'd go ahead and shade in this way and then probably even darken in the arrow. So all the numbers that are bigger than or equal to 2 are solutions. All right, and then our second problem here. One of the special things that happen with inequalities is going to come up here while we're solving this. So we're solving for x again. We need to get rid of this 13, subtracting 13 on both sides. We get negative 2x is less than 12. And then to solve this, I actually need to divide both sides by negative 2. Anytime I do this, anytime I divide both sides by a negative number or multiply both sides by a negative number, I actually need to switch the direction of my inequality. So right now we have a less than symbol. We're going to switch that to be a greater than symbol. And here is our answer. X is greater than negative 6. Now, why does this happen? Let's just look at a quick example here. Let's just say we have negative 10 is less than 5. Certainly, you guys can agree that this is true. But if, let's say, I multiply both sides of this by negative 1, the rules for multiplying and dividing by negatives are the same. So, right, two negatives that multiply by each other or divide by each other end up creating a positive. And then a negative and a positive create a negative. But when I do that, this inequality is no longer true, right? But what makes it true is just switching the direction of my inequality. If I switch the direction of that inequality, it is true, always will be true. So that's just a quirky property of inequalities that we have to keep in mind as we're solving them. Anytime you divide or multiply by a negative, you need to remember to switch the direction of your sign. Okay, and now we want to graph that. So I'll go ahead and graph in red, greater than negative 6. So negative 6 is here. This is a strict inequality, meaning we're not including negative 6. So we use an open circle there. And then we shade to the right here, shade to the right, anything greater than negative 6. So everything to the right. All right, and I'm going to go ahead and erase those down there because it's getting a little messy. All right, now the last one, we have what's called a compound inequality. So we're going to solve all three parts of this simultaneously. I'm going to try to get x all by itself in the middle and see what happens on the ends here. So anything I do to this middle part to cancel things out, I need to do to both ends. So I'm going to be adding 7 on both sides of this. I say both sides, all three sides, all three parts of this. 9 plus 7 is 16. It's less than 4x. Is less than 28. And now we need to divide both sides. And by both sides, again, I mean all sides by 4. So we get 4 is less than x is less than 7. Now I did not divide by a negative here, so no need to change the direction of my inequalities. And this right here is going to be our solution. So this is saying that x is between 4 and 7, not including those. There's no or equal to. These are strict inequalities. So x has to be between 4 and 7. 4 here and 7 here. And all of the values in between those are solutions. So that's actually a narrow range of solutions. And again, we do not include the ends. So we use these open circles to demonstrate that 4 and 7 are not solutions. Yeah, great. Clear this off, and we're going to move forward to talk about triangles. All right, so here's some objectives for this lesson. We're going to be trying to list the sides and angles of a triangle in order based on the length or measure. So from smallest side to biggest side, from smallest angle to biggest angle, or we could go the other way. And then another one is to determine the side lengths that are necessary to create a triangle. So we're going to say, for instance, we may be given 3 side lengths. We need to know if we can actually use that to make a triangle. And the third one that I'm going to go through in this video is not required, but we're going to talk about indirect proof and how to demonstrate simple properties of triangles and such using this concept of indirect proof. All right. So here's some quick things about notation. So sometimes we use lowercase letters like this to denote a side. So if we want to talk about this side, we could use a lowercase k because it's across from the uppercase angle k, or in this case, f. We could use a lowercase f to talk about this side. So likewise, kind of continuing that, right? If this is angle M, then across from the triangle here is side M. If this is angle E, then across our triangle, we call that side E. Kind of finish that out in the other triangle, right? If this is angle J, then this hypotenuse here could be side J. If this is angle L, we could call this side L. Sometimes that gets used, just something to notice. All right, so here is the angle-side relationships in a triangle. This is a theorem that we have. So it says that if 2 sides of a triangle are not congruent, then the larger angle is opposite the larger side. This actually is a pretty simple relationship here. So basically what we're saying is these 2 sides in our triangle here, A, B, and BC, are not equal to one another. So we can look at the angles to determine which side is actually bigger. Or we can look at the sides to determine which angle is bigger. So in this case, this side, AB, is greater than this side, BC. Therefore, the angle that's across from AB, so angle C, is bigger than the angle that's across from side BC, which is A. So the bigger angle is across from the bigger side, and subsequently the smaller angles across from the smaller side. So let's go ahead and take a look at this triangle here down below. Which angle is greater? Angle M or angle P or angle R? Okay, well, we're going to do that by looking at the sides. So angle P is across from a side that is 21, and angle R is across from a side that is 17. Since 21 is greater than 17, so since this side, RQ, is greater than PQ, we can say that the measure of angle P has to be greater than the measure of angle R, because P is across from the bigger side than R. Pretty simple idea. And this works within a singular triangle. If we have 2 different triangles, we can't really compare using this relationship. But inside of one triangle, we can compare the sides and angles using this relationship. So this was one direction. We can also go the other way. That was saying if the sides are unequal, we can use that to determine the relationship between our angles. We're going to do the same thing. If the angles are unequal, then we can use those to compare the sides. So if 2 angles in a triangle are not congruent, then the longer side is across from the larger angle. Pretty easy to say, right? So in this picture, angle Z is bigger than angle Y. So the side across from Z is bigger than the side across from Y. Pretty easy. All right, let's go ahead and look at this problem, try to apply that here. So which side is longer, DE, which goes from here to here, or VE? So VE goes from here to here. Well, we don't know everything we need for this problem. We actually have to do a quick little calculation here to figure out the measure of angle V. So adding those two together, 48 plus 87, you always use the triangle sum theorem, so you need to make sure to keep that in mind anytime you're doing these problems. So those add to 135. So we take 180 minus 135, and we figure out that this is 45 degrees. So here is a 45-degree angle at V. Okay, so we can use that then to compare, we can use the angles to compare the sides. So 45 is across from DE, and 48 is across from VE. So the bigger angle is going to be across from the bigger side. So in this problem, VE is greater than DE. Again, because 48, so because 48 degrees is greater than 45 degrees. So that's really it. And the 48 is across from the VE, and the 45 is across from the DE. So we use those to compare them. Pretty simple, really. It's just a matter of making sure we're careful and knowing which sides are across from which angles and comparing those. All right. So let's go ahead and take a second and try to do these problems. Feel free to pause the video because I am going to go ahead and start doing them right away. But try to list the angles in order from smallest to largest in this triangle, and write the sides in order from shortest to longest in this triangle. So go ahead and pause and do these problems, and then restart it here. All right, so we are going from smallest to largest. So we want to identify the smallest angle in this triangle. So the smallest angle is going to be across from the smallest side. Looking at our three sides, smallest side is 9. That means the smallest angle will be angle B. That is going to be our smallest angle. So angle B is the least, so it'll have this symbol here in front of it. And then what is the next biggest angle? Well, the next biggest angle is going to be across from the next biggest side. So 9 was the smallest. We can ignore that one. The next biggest side here is 15. So that's going to tell us that angle A, which is across from that 15, is the next largest size. So angle A is kind of in the middle here, and it's going to be less than the biggest angle, which is angle C, right? Angle C is going to be the greatest because it's across from the greatest side. So angle C will be the largest. So we ordered them from smallest to largest, and I'm using these inequality symbols to compare them. Maybe too many of them here. So, remember inequality symbols, that the hungry alligator is eating the bigger quantity, and its backside is facing the smaller quantity. So the smallest in this case has the backsides all pointing to it, B, and the big hungry sides are facing the largest angle here, angle C. Perhaps I didn't have too many symbols there because this was supposed to be a less than symbol, and this is supposed to be an angle symbol. Maybe I just wrote a poor angle symbol. There we go, angle C. So anyway, largest, smallest, middlest. All right, second problem here. Again, if you haven't done this one yet, feel free to pause it and try it. We're going to be using the angles to rank the sides from shortest to longest. In this problem, we do need to know this angle here. These two angles are complementary because it's a right triangle. They have to add up to 90, so that's going to be 70, 68 degrees for that. Those two would add to 90, and 90 makes 180. So anyway, we want to go from shortest to longest. So the shortest side is going to be across from the smallest angle. So shortest side is EF. So EF is the shortest. Then what's next? The next biggest angle is 68 degrees E, and that's across from DF. And the longest side is going to be across from our right angle here, DE. DE. Obviously, we could have named these differently. That's the naming that I chose for them. We could have called it FE, or even used that naming that we learned about early on today and talked about these in terms of D, E, and F. Right, this side would be D, this side would be E, and this side would be F if we wanted to use those lowercase letters to talk about it. However you name them, it doesn't really matter. We just want to know which ones they are. All right. So the next thing that we want to do here is talk about what's called the triangle inequality theorem. So the triangle inequality theorem is a pretty simple idea that has some interesting applications. So it says that the sum of any two side lengths of a triangle is greater than the third side. So if we know three numbers for a triangle, so 3, 4, 6. So say these are the three side lengths for a triangle. It is true that if I add any two of them, so 3 plus 4, which is 7, is greater than 6, right? That checks out. 3 plus 6, which is 9, is greater than 4. And 4 plus 6 is greater than 3. Yeah, so all of those things check out. So these three numbers could be used for the side lengths of a triangle. If any one of these does not hold up, then we cannot make a triangle. And so if you look down here at this little animation, you can see that these three side lengths that we have, the two pencils and the eraser, they can't be used to actually make a triangle. And you can really see that here, where they're too short. They don't actually meet in the middle. They have this side here, and they're just not long enough to actually touch, no matter what. They're too short. They need to be at least a little bit bigger than the third side. Otherwise, they won't actually meet and form a triangle. If all three sides, well, if the longest side and the two shortest sides actually add up to be exactly equal, you still won't be able to. These two shortest sides do need to be bigger. Otherwise, they just won't quite meet up. They'll only be able to lay exactly on top of each other, but they actually won't make a triangle. Let's actually look and see what we can do with this, though. So first one, this is pretty straightforward. Can these side lengths make a triangle? I'll give you a little hint here. You can try this on your own. Pause it right now, but yeah, go ahead and pause it right now and see if you can answer these, and then we'll go ahead and I'll go ahead and start doing the problems. All right, so turns out you really only need to make sure that the two smallest sides add up to be bigger than the third. That's really the only one that matters. So we want to make sure that 6 plus 14 is greater than 18. 20 is greater than 18. We're good to go. We know the rest are going to work. If I do 14 plus 18, that's way bigger than 6. If I do 6 plus 18, that's way bigger than 14. So I only really need to test these two, the smallest two sides. So this one is a yes. You can make a triangle with these side lengths. Second one, no. Because if I add the two smallest sides, 2 plus 6, it is not bigger than 9, because 8 is not bigger than 9. So this is a no. We cannot make a triangle with these side lengths. We would have a 9, we'd have a 6, and we'd have a 2, and they wouldn't quite meet. There'd be no way for those two to meet. They'd just be too short here to meet in the middle. So we wouldn't actually be able to make a triangle. All right, so let's go ahead and use this in a slightly different way. What we're going to do here is, instead of deciding whether we can make a triangle, we're going to say we have a triangle, and we know two of the sides. What's a range of possibilities that third side could be? What's sort of the smallest it could be? What's the biggest it could be? And we know that it's going to fall somewhere between there. So what we need to do here is actually set up two inequalities. There's two cases here. The first case is, let's see how small it could possibly be. In this first case, it is one of the two smallest sides, either the smallest or the second smallest. It doesn't matter which, but it's one of the two smallest sides. So this is our first case. So we'll just assume maybe it's the smallest side, but sometimes it won't be the smallest side, which we may see in some examples here. So if it's the smallest side, let's go ahead and call it x. That means that x plus 12 needs to be greater than 19. This inequality needs to hold. That's our first case. We'll solve that one in just a second. Our second case is, well, what if that side is actually the biggest side? So biggest side. In that case, then I know that if I add these two smallest sides, it has to be bigger than x. The two smallest sides always have to add to be bigger than the biggest. So if it's the smallest, I'll add it with this one and make sure it's bigger than the biggest. If it's the biggest, I'll add the two smaller sides and make sure it's bigger than x. And solving these two inequalities are going to give me my solutions, right? So I'm going to subtract 12. And this is telling me that x has to be bigger than 7. So 7 is the lower bound. It not equal to 7. 7 doesn't work, but something bigger than 7, like 7.1, 7.2, 8, 15, something like that would be bigger than 7. And then here to solve this one, well, I just add those together. We get 31. So in this case, x has to be bigger than 7 and x has to be smaller than 31. So we actually have a compound inequality that sets a range of values for x. X has to be between these two values, greater than 7, right? The alligator's eating the x, so x is greater than 7, but x is smaller than 31. The alligator's eating the 31, it's the bigger quantity. But again, we don't include the extremes here. It could go all the way up to 31, but not be 31. It could go all the way down to 7, but not be 7. But we could get as close as we want and still make a triangle between 31 and 7. All right, let's go ahead and try one more. Again, feel free to pause it when we get here, just so that you can try it on your own. So we're using the triangle inequality theorem to find a range of distances between Mason and Austin. So we're talking about the side of the triangle that is right here between Mason and Austin. It's hard to see that maybe, but right there, a kind of double green line that I made. Basically, it's a triangle, right? We have two known sides. We want a range of possibilities for the third side. So we have to examine our two cases. Again, feel free to pause and try this on your own, but I'm going to go ahead and do it. Our first case is that this side, this unknown side, is the smallest, or really one of the two smallest. It doesn't really matter if it is the smallest. In that case, x plus the other small side, 78, has to be greater than the big side, which in this case is going to be 111. That's our first case. The other case is, well, what if it's the biggest? Well, if it's the biggest, the other two are the smallest. So we add those other two known together and say that they have to be bigger than x. That's our two cases, and that's going to set the range of values. So we subtract 78. And we say that x has to be greater than 111 minus 78. 33. So x has to be bigger than 33. And then I add these together, and I get 189 has to be greater than x. So this sets our range of possibilities. X has to be bigger than 33 miles. And x has to be less than 189 miles. So the distance between these two cities falls somewhere between these numbers. Obviously, this is a really big range and doesn't really help us so much in the particular map problem, but it is an application for the values based on the triangle inequality theorem. All right. So from here on, this is some indirect proofs. I'm actually going to stop this and make this its own video. So see you guys later.